Hello students, welcome to lecture 3 on the online course of Introduction to Microwave and Optical Metamaterials. Today's lecture will be on applications of optical metamaterials and some classifications of metamaterials. So, here is the lecture outline. We will look into the applications of optical metamaterials such as artificial chirality, cloaking and imaging. We will revisit some fundamentals on the classification of metamaterials based on the material properties, but this time with more understanding based on the previous lectures. And we will also do metamaterials classification based on functionalities such as electromagnetic metamaterials, acoustic metamaterials, thermal metamaterials and mechanical metamaterials. So, this is just to give you an overview that this metamaterial field is really vast and you can use metamaterial concept for different applications. So, let us take this first example of optical metamaterials which can produce artificial chirality. Now, chirality basically refers to the geometric property of a structure lacking any mirrored symmetry plane. So, here is an example of chiral object. So, if you take your left hand and place it before mirror, okay, you will see your right hand, right. So, you try to superimpose your left hand and right hand, you will not be able to do that, okay, because of this property called chirality. So, chirality basically exists in many forms in nature, starting from molecules to proteins and to crystals. Okay. So, even this particular example shows you that we also have chiral objects with us. In contrast, a structure is called achiral if it is indistinguishable or you can properly superimpose the object on its mirror image. Now, chiral geometries can produce intriguing optical effects, some really exciting optical effects, something like circular birefringence or optical rotation, or even it is called polarization rotation, which is basically the rotation of the polarization of linearly polarized light when it travels through a chiral material. Okay. And this rotation basically happens because the material has different refractive indices for the left and right circularly polarized light. So, birefringence means two different refractive index values, right. It also shows another important property called circular dichroism, which is basically the differential absorption of the left and the right circular polarized lights. Okay. So, a very strong optical activity can be seen in metamaterial system consisting of metamolecules that themselves are not chiral, okay, but still because of the orientations you can create the artificial chirality in it. So, here is such an example. So, you take a planar metamaterial which is based on an array of asymmetrically split rings. Okay. When I say asymmetrical split rings, you see the two rings are not identical. Okay. One is a larger arc, another is a smaller arc. Okay. So, they can manifest optical activity and circular dichroism at oblique angle of incidence. Okay. So, what happens? Let us first define the direction of asymmetry, which is represented by a polar vector S, as you can see here. Okay, you can see here as well. Okay, so this vector basically goes from the long to the short arc. Okay, and optical activity is seen when the metamaterial plane is tilted around the x axis, as you can see here. Okay, so that the sample normal n and the incident wave vector k, they form a non-zero angle, which is shown here and here. So, this is for the case of normal incidence, okay, but these are the two cases where the sample normal and the wave vector, they are forming an angle. Okay. So, in this case alpha is, so here also you can see alpha defined like this. So, here alpha is positive, here alpha is negative. So, you are basically getting two configurations, right. So, configurations with plus minus alpha are called enantiometric arrangements that shows optical activity of opposite signs, right. Whereas, you take this particular configuration which is alpha equals 0, that is for normal incidence, and that will not show any optical activity. Now, this is particularly the unit cell that is used for metamaterial that works in microwave regime. So, you can see the dimensions are typically in millimeters. Okay. So, this is basically a asymmetric split ring structure, which is a complementary structure. That means, you are basically not making the ring, you are basically removing the portion. So, these are basically complementary structure which is made out of 1 mm thick aluminum sheet. So, you are just making apertures like this, and that is giving you the unit cell. When you want to see the same thing in optics or optical frequency, so you are going to make optical metamaterials. So, there you have to work with a glass substrate, typically 500 micron thick glass substrate that you take. This is the periodicity. All the parameters are now of the order of nanometer. That is where the optical wavelength lies. Okay. So, you start with a 50 nanometer thick aluminum wire which is placed like this to form your asymmetrical arcs. Okay. So, here are the results of this particular structure. So, first we will discuss about the left one. So, it shows circular birefringence which is delta phi in degrees, and also the dichroism which is delta given in dB, okay, which are observed in the transmission for different tilt angles. So, we considered here alpha plus 30 degrees and alpha minus 30 degrees, and for reference the non tilted case of alpha equals 0 is also shown, right. So, this is for the microwave metamaterial which is measured in an anechoic chamber using broadband horn antennas. You can see the range of frequencies, and this is detected using vector network analyzer VNA, right. And this is on the right side, you see the photonic structure. So, everything now is for optical metamaterial. So, you are basically looking at wavelength range starting from say 800 to 2000 nanometer. Okay. So, this structure is the of the unit cell. It is measured in a microspectrophotometer using linear polarizers and a super achromatic wave plate. So, here also you can see alpha equals 0 gives you a flat line, no birefringence, but for alpha plus 20, that is the red ones, alpha minus 20 the blue ones. So, you can see birefringence, and also you can see dichroism happening, right. So, with that we move on to the next application of optical metamaterials, which is also very exciting, and that is of cloaking. So, as I mentioned in the previous lecture, that you can make artificially structured metamaterials that have enabled unprecedented flexibility in manipulating electromagnetic waves, and they can produce new functionalities such as cloak of invisibility based on a concept called coordinate transformation, right. So, this particular figure we have seen earlier, it shows you the first experimental demonstration of a cloak was at the microwave frequencies. However, the main idea of invisibility will be in the optical domain. This is also particularly important. The microwave cloaking is also particularly important for stealth applications which are part of the modern warfare. Okay. So, here I believe all of you remember that when you keep this solid object within this particular cloak, okay, light rays or microwave radiation are made to go around this object, and they emerge out of the cloak as if there is nothing disturbing in their path. Okay? That means this object that you are putting in within the cloak is basically becoming invisible. Now, the same design cannot be implemented for an optical cloak. However, optical cloaking and the true invisibility cloaking is very exciting, and people have been trying this for many decades. So, here is an prediction, or you can say schematic, how you want the invisibility cloak to look like. So, there is a lady holding this kind of a cloak which makes her invisible in the part where the cloak is covering her body. So, you can see the tree and the background through it. Okay. So, there is nothing that is blocking the light, and this cloak is very challenging because you need to achieve this cloaking not only at a particular frequency, you have to have it for the entire visible light wavelength range and also for all the angles. Okay. So, that makes this invisibility cloak really challenging. So, if you remember how things were done, so you need to use the concept of coordinate transformation. Okay, that is needed, that is also part of this transformation optics, which will go into details later on. But you can see what we are trying to achieve here, that the coordinate transformation is basically used in the proposed optical cloak of cylindrical geometry, where the region of the cylinder ranging from r less than b, that is this entire thing has to be now mapped within this particular concentric shell, where r is between a and b. Okay. So, all these things have to be mapped here. So, that means whatever you will be keeping inside will not have any effect on the electromagnetic waves. So, this recipe looks very similar to the cloak that was developed in the microwave regime, right. So, you can also think of it in this particular way, that a small fraction of the cylindrical cloak can be thought of where the wires are all perpendicular to the cylinder's inner and outer interfaces, but the spatial positions need to be periodic, okay, do not have to be periodic, and they can be random. Okay. And for large cloaks, you do not need to have this kind of continuous wires. You can have the wires broken into small pieces that are smaller in size as compared to the wavelength. Okay. So, the actual unit cell, the cylindrical sector encapsulating a spheroidal silver wire. Okay. So, this is a silver wire in a dielectric host. Okay. So, you can look into the geometry like this. Okay. So, it is a 3-dimensional rectangular unit cell. So, you have the parameter like HC and LC, and WC is basically the width that will change in proportion to the radius in each layer, right. And if you see, the red one shows the initial unit cell, that is basically the cylindrical segment, and from that you can actually find out what will be the effective unit cell that will give a rectangular prism kind of shape, right. So, here are the results of electromagnetic simulation that shows magnetic field mapping around the cloaked object. So, this is the object that is being cloaked. So, this is basically that cylindrical cloak that have been applied. So, this is under TM illumination, and you see the way the waves are propagating. After this cloak also the waves propagate in a similar fashion. However, without the cloak, okay, that is shown in figure B, you can see that this hidden object, which was actually in metallic cylinder of radius A, the cloak is not working here. So, it is basically blocking the electromagnetic wave in its path, and it will get automatically detected, right. So, to illustrate the performance of the proposed optical cloak, this field mapping simulations were performed using commercial simulation package of COMSOL. So, what it shows that when you have the cloak, the wavefront flows around the cloak object, but without the cloak the waves basically get severely distorted in these regions, and that is why it basically casts a shadow behind the cylinder, right. So, when you put the clocking, it basically shows the capability of reducing the scattering from the object hidden inside the cloaked region. Next important application is in the field of imaging. So, metamaterial and metasurface, which are basically the two-dimensional counterpart of the metamaterials, they are very useful in imaging applications, and this spans across the electromagnetic spectrum. So, we can start with the first column, where you can see radio frequency. Okay. So, these are basically metamaterials for enhanced magnetic resonance imaging applications. Okay. The upper panel here shows a larger split ring resonator array combined with a varictor diode that is inserted in the gap, that serves as a nonlinear element to turn on and turn off the resonance of this array. Okay. So, the middle panel here shows that when you keep an onion sample for doing MRI, magnetic resonance imaging, on top of these things, the signal to noise ratio gets enhanced, whereas if you remove this array, the metamaterial array, the signal is like that. So, you can see the signal to noise ratio enhances multiple times, right. Moving to the next one, you can see metamaterial aperture for millimeter wave computational imaging. So, the upper portion of the figure shows a metasurface transceiver panel tilted with both transmit and receive metamaterial components. Okay. The lower portion basically shows an image of a mannequin observed using the metamaterial panel in conjunction with computational imaging methods. So, this is useful for full body real time imaging. The next column shows you the complementary metal oxide semiconductor terahertz imager at room temperature, which are using metamaterial absorber. So, this particular upper panel displays a portion of the imaging array. So, the pixel pitch here is roughly 30 micron, and the lower panel basically shows the image of letter T, as you can see. Okay, that is obtained through an opaque envelope. So, this is used for high resolution opaque imaging. So, you do not need to open up the parcel, you can actually image the object inside. Okay. The fourth column here shows metamaterial enhanced pyroelectric infrared detector. So, the upper panel is basically a scanning electron microscope image of the portion of the detector. Here you can see the bar, which is representing 20 micron. So, this is an absorber that comprises of ground plane, lithium niobate and a metasurface layer. Okay. And this lower panel here shows the enhanced detector response coincides with the enhanced metasurface absorption. So, with the metasurface you can have much better detection, okay, and also you can get wide field of view. Okay. And the last panel here shows multiplexed nonlinear metamaterial holography. So, the upper panel basically shows a region of the metamaterial that encodes the hologram, and the lower panel basically shows images obtained for different combinations of helicity of the incident light and the detected second harmonic light. So, here you can see left circular polarized and right circular polarized. This one is for RCP LCP, this is LCP LCP, and this is RCP RCP. Okay. So, all these different computer generated holography with the aid of metamaterials are possible. Okay, so with that we move on to the classification of metamaterials, which you have seen already in the first lecture, but now with a better understanding we will go into little bit of more details. So, the classification, this epsilon and mu diagram is very popular in this field of metamaterials. Okay, they represent the permittivity and permeability, and the electromagnetic responses of any material can be represented in this particular space. So, we are basically plotting the real part of the permittivity epsilon r and the real part of the permeability mu r. Okay. So, all the combinations of epsilon r and mu r can be placed in this parameter space. The conventional dielectric material typically falls in the first quadrant, where both epsilon r and mu r are positive, and we have seen that noble metals like gold, silver, aluminum, okay, they are the noble metals at optical frequencies, and they are good examples of materials with negative permittivity. Okay, and they are basically here, and the ones with negative mu can be found in the ferromagnetic medium near the resonance, but there is nothing in this particular regime. So, what is happening that in the second and the fourth quadrant, okay, because you have imaginary refractive index coming up, so the waves are basically not allowed to propagate. So, you get evanescent waves, right. So, I believe all of you understand how refractive index is calculated for epsilon and mu. So, n equals plus minus square root of epsilon and mu, right. So, depending on whether the product inside the square root is positive or negative, okay, you take the positive or the negative square root, right. So, that is what is happening in these two cases. So, when one of the parameters is negative, the index of refraction becomes purely imaginary, okay, and that is the case where you will have only evanescent waves. And in the domain of optics, all conventional materials are confined to an extremely narrow zone that is given by this horizontal line that marks mu r equals 1, and that is the case that in optical metamaterial will just work in this particular area. Okay. So, once again we have seen this diagram, but just for a quick recap, the top right quadrant where both are positive, it is called double positive metamaterials or double positive materials. Okay. So, these are most occurring media such as dielectric fall in this category. This one has, these are kind of quadrant where epsilon is negative, so you can call it epsilon negative material. So, in certain frequency regimes many plasma exhibit these characteristics. You can think of an array of metallic wires giving you this. But the bottom right quadrant is where permittivity is positive, but permeability is negative. So, you call it mu negative material. So, in certain frequency range some gyromagnetic material exhibit these properties, and the third quadrant, which is where both epsilon and mu are simultaneously negative. So, you can call them also as D and G, double negative material, and this class of material has to be only produced artificially. So, this is the true metamaterial section, right. Now, you can also do the classification of metamaterials based on their functionalities. So, you can put them in 4 categories typically. The electromagnetic metamaterials, as we have described, they can have applications in cloaking as absorbers in terahertz application. You can think of acoustic metamaterials. There also you can make acoustic cloaks, absorbers, and for focusing acoustic waves. You can think of thermal metamaterials, which can control the heat flux distribution, control the thermal emissions, and also do cloaking. Okay. So, you can hide an object's thermal signature or mimic something else signature, which is also used for thermal camouflage kind of application, which is very important in modern warfare. And finally, you have mechanical metamaterials, which are very useful for impact reduction or energy absorption, things with negative Poisson ratio and minimum shear modulus. So, a lot of classifications can be done based on the range in or based on the domain or functionalities where metamaterials are basically functioning or working. So, this is called classification based on its functionalities. But in this course, we will be focusing only on electromagnetic metamaterials, that too particularly working in the microwave and optical frequency range, right. So, the classical behavior and features of electromagnetic metamaterials we have seen already. They are giving us negative refractive index, they are useful in imaging and cloaking. So, other than these classical ones, okay, there are some emerging classes of metamaterials which are called information metamaterials, intelligent metamaterials and quantum metamaterials, which are basically paving the way for the next generation applications in modern advanced communication systems, sensing technologies and beyond. So, let us look into information metamaterials. So, in the classical regime, traditional electromagnetic metamaterials have limitations of fixed functionalities that once they are made, they just perform in the same way, and there is no way to control the electromagnetic wave in real time. You cannot change the behavior of the metamaterial. So, to overcome these restrictions, information metamaterials, which includes digital coding and field programmable metamaterials, have been recently proposed that could enable real time manipulation of electromagnetic waves. So, information metamaterials will enable real time manipulation of electromagnetic waves and direct digital information processing, and further they will help you to realize information perception, understanding, memory, learning and even cognition. So, at the same time they also provide a physical platform to achieve more flexible, real time and intelligent electromagnetic wave manipulation, and that is very important. So, if you take example of digital coding metamaterials, so coding metamaterials basically contain a finite number of elements and manipulate electromagnetic waves by virtue of discrete coding sequences. Okay. So, the initial coding metamaterials consisted of two basic elements of different structural dimensions corresponding to the coding states of 0 and 1. So, that means with 180 degree phase difference. Okay. So, here you can see that each element can be either 1 or a 0. So, this is the schematic of the coding metamaterial, which has got two types of elements 0 and 1, and this particular B shows the geometry of the coding element and the corresponding 1 bit reflection phases. So, this is for the phase, this is the phase of the 1 element over the frequency range, and this is the phase of the 0 element for this frequency range, and this is their phase difference. Okay. So, this particular inset shows the coding element, which is mainly a square metallic patch on the top layer, and it has got a dielectric substrate in the middle layer, and again there is a metal ground plane on the bottom layer. So, just for information, the substrate has a thickness of around 1.964 millimeter with dielectric constant of 2.65, and it has a loss tangent of 0.001. The metallic patch has a thickness of 0.018 mm, width is W, and the periodicity is typically A, which is 5 millimeter, and these patches are designed with width of 4.8 and 3.75 millimeter, and that is where the phase difference of approximately 180 degree is obtained in the broadband. Okay. So, here the frequency range of interest is from 8.1 gigahertz to 12.7 gigahertz, where you can have around this 180 degree, around 180 degrees. So, exactly 180 degree phase difference is there at 8.7, 8.7 and also at 11.5 gigahertz, right. So, you can use the patch particle with width say 4.8 millimeter as 0th element, and when you change the width to 3.75 millimeter, that can be used as one element. Okay. So, they can be easily fabricated in a single layer dielectric board, and you can construct this particular meta surface. So, you can take this further, that when you take the coding pattern to be all zeros or all ones, so in that case you can get only one single reflected beam from the board. Okay. But if you change the coding pattern to 0 1 0 1 like that, okay, so that means you are basically having, you know, this kind of a design. Okay. So, 0 and then 1, 0 and then 1. So, you are basically getting two symmetrically reflected beams generated. Okay. And if you change the coding pattern to a checkerboard kind of distribution, okay, in that case you will be able to generate 4 symmetrically reflected beams. So, the same surface can give you different optical response in real time based on the coding that you are doing. So, this kind of 0 and 1 possibility, so they are also called 1-bit metamaterial structure with periodic coding sequences, and they are verified using analytical and full wave simulations. So, if you choose the coding sequence to be all zeros, so it is like a plain metamaterial of the same element. So, it is just giving the reflected beams in this direction. Okay. So, this is the near field distribution, the top row, and these are basically the far field scattering patterns for different coding sequence. So, when you have 0 and 1 grating kind of, so you get 2 beams, and then when you go for checkerboard kind of design, which is basically periodicity in both x and y direction, you will get 4 symmetrical beams, right. So, this is how you can make digitally encoded metamaterial surfaces. So, with that we will conclude this lecture. We will start discussion of classification and metamaterials and overview of the metamaterial technology in the next lecture. Regarding this lecture, if you have got any query, you can email to this particular email address mentioning the course name and the lecture number on the subject line. Thank you.